Okay, welcome everyone to a new edition of the PYSQT seminar. I have the pleasure to present as the speaker for today, my friend Mateo Uldemonlins. He studied physics at Zaragoza. Then he moved to Paris for his Erasmus, and he liked it so much that he stayed there to do his master's at ENS, and then to do his PhD at PYSQT. He recently defended his PhD thesis, and today he's going to give us an overview of his work. Mateo, whenever you're ready.
Okay. Well, thanks a lot for the interaction, Juan, and for having me here. So yes, indeed, as you said, it's already quite some time ago that I left Spain and to just slowly get back into the research community there and see this initiative. So, which is, I find it's very nice. So today I will present you this work that is part of my PhD, and I would like to walk you through backwards in the title. So I will start by presenting just the very basic ideas of superconductivity. Then I will introduce what are these Yu-Shiba-Rusinov states that, as we will see, are closely connected to impurities in superconductors. And then for the last part, I will present you this quasi-particle focusing effect that was the work we did in this field. So if Juan agrees, I like to keep this as informal as possible. So if there is something I say is not clear or I don't express myself properly, just please interrupt, and I'll be happy to try to answer. And also if I mess up with the microphone and at some point this becomes inaudible. Okay. So as a starting point, I thought it was perhaps a good idea to just recall what we all know, namely what are superconductors. So as you know, superconductivity, it can be understood as a phase of matter, as an emergent phenomenon that occurs typically at very low temperatures. So these very low temperatures usually means that we need to go to liquid helium temperature in order to enter this superconducting phase for most metals and materials. And so, you know, superconductivity is characterized by two fundamental properties at the microscopic scale. The first one is perfect resistivity, or zero resistivity, sorry. So this is represented in this experimental plot that I'm sure you've seen before. This was the result, the observation made by Carl Ons in Leiden in 1911, the first observation of superconductivity, and it's showing the electrical resistivity of mercury as a function of temperature. And so the observation is that it goes linearly with temperature, and at a certain critical temperature, there is this huge drop in magnitude that signifies the superconducting transition. And so the other important property at a macroscopic scale is the so-called Meissner effect or perfect diameter. That essentially tells us that if we have a sample that is immersed in a magnetic field, and we cool it down so that it enters the superconducting phase, it's going to expel these lines of magnetic field, and therefore we will observe it that it levitates. So here, by the way, let me just tell you that this demonstration that we usually see in science fairs, it's done with a ceramic superconductor that need a lower temperature. So usually it suffices to pour some liquid nitrogen so that we see this Meissner effect. But again, I emphasize that for conventional superconductors, we need to go much lower in temperature. And so these properties are very fundamental, and also they have very important industrial applications, you might say. But here in this talk and in my PhD, I was rather interested in the behavior at the microscopic scale. So that means precisely how do electrons behave in this superconductor. And for that, it's best to look at superconductivity through the framework of the BCS theory, where these fermionic degrees of freedom are going to appear explicit. So this BCS, it stands for Bardeen, Cooper, and Schrieffer, that are the researchers that propose this first work in microscopic theory. And I was published in the late 50s. As you can hear, this is the original. And so I will not go through the details of this BCS theory. I think this is not the moment to do it here, but just let me recap very quickly three key ideas that will be useful for the rest of the presentation. The first one is that the minimal ingredient that we need in order to trigger this superconducting phase is to have an effective attractive interaction between electrons, or more precisely, between time reversal states. So in the case of conventional superconductivity, it's usually assumed that this effective attractive interaction is mediated by lattice, by phonons in the lattice, and it's essentially pairing electrons with opposite momenta, k and minus k, and opposite spin up, spin down, that are living in the vicinity of the Fermi surface. Okay, and this is what we represent typically with this scattering potential. Again, the fact that your time reversal states, as we will see, is very important. Now, it turns out that the Fermi surface is unstable against this attractive pairing, and so the ground state of the system becomes a many-body coherent superposition of Cooper. So this is a rather complicated many-body quantum state. But for us, the key point is that excitations over this many-body ground state are single particle excitations, and they are seated at an energy of 2 delta above this many-body. So that means that when we look at the density states of excitations, we are going to find a gap of 2 delta around the Fermi. Okay. The fact that this excitation spectrum is gapped can be very easily probed with a scanning Tulip microscope. And this is the result of such an experiment. And so let me just quickly walk you through the plot as we will encounter it later in the presentation. So essentially here we have the bias voltage in the horizontal axis. So that is the voltage difference between the sample and the STMT. And in the vertical axis, we have this differential conductance that is proportional to the density states, the excitation density states in this. And so what you see that here around 0 bias voltage, which corresponds to the Fermi level, you see that this curve is at 0, meaning that there are no available states into which we can tunnel. And in other words, that the density states is essentially 0. Okay. Very cool. So in this talk, I will be mostly interested in discussing what is the effect of impurities in these conventional superconductors or S-wave superconductors. Impurities, as you know, are simply exogenous atoms that break the periodicity of the crystalline lattice. And historically, they have been an important topic, mainly because they are present in samples in nature, as we find. Okay. So for the case of a finite concentration of impurities, there are 2 fundamental results in superconductivity. The first one is the so-called Anderson theorem that tells us that conventional superconductors are mostly robust against small amounts of this non-magnetic impurity. And the way we can understand that is that even though we are going to have these impurities that are going to mix our block states, this attractive interaction is going to be effective because we are still going to find this degenerate time reversal state. So we can effectively pair them even though they are not anymore block states. So we can essentially write the same VCS theory with these new eigenstates of the disorder Hamilton. Here you have an example of this fact or this theorem. You have on the left panel topography of a very disordered material. So these blobs that you see here in white, brighter color, those are these defects, it's non-magnetic impurities. And when we measure the DADV curve as a function of bias, we see that we have the nice superconducting gap as predicted by the DC. Now, if we fix the bias at 0 energy, and then we scan over this surface, which is what we are representing in this middle panel, you see that the DADV is essentially 0, here as indicated in this color scale, meaning that indeed, if we look at the gap, this sample is essentially homogeneous, even though there are all these many impurities. Now, on the contrary, it was shown by Abrikosov and Gorkov that if you consider magnetic impurities, those will affect superconductivity, and in fact, they are detrimental to it. And this, by the same logic, it can be argued that it's because they lift this time reversal invariance. Here you have yet another experimental plot of this observation. So you have the DADV curve again as a function of bias. Here, please note that it's just half of it. And each of these curves is for a given impurity concentration of manganese impurities that are magnetic because they have a local. So you see that whereas 0 concentration of these impurities, we have the nice superconducting gap, the blue curve here. And as we increase it, the gap is depleted and eventually superconductivity is killed. Okay, so there are these two results. Non-magnetic does not affect, magnetic kills superconductivity. Now, in view of this result, is a natural question to ask: what happens in the limit of a single magnetic impurity? Okay, and then it was shown by Yu-Shiba and Rusinov already in the 60s that this magnetic adatom is going to act as a pair breaking defect. So you can imagine that, as I said before, our Cooper pairs are going to be composed of spin up and spin down electrons, and you can imagine that this local moment of the impurity is going to tend to misalign the spins in the Cooper pair, and then it will locally break these Cooper pairs. As a result of this pair breaking effect, we are going to find that there are in-gap excitations that are localized on the impurity. And so these in-gap excitations are what we call Yu-Shiba-Rusinov states in honor of these researchers, and this will be the object of this talk. So this, as I said, was predicted in the 60s, and it was observed for the first time in 1997 by the group of Alicia Dani in Princeton with an STM again. And here you have a summary of this experiment. So on the left panel, you have the DADV curve. I recall this is essentially the excitation density states far away from the impurity. So you see that we have this very nice superconducting gap and the fit to the BCS theory that agrees very nicely. Now, in the middle of the panel, we are representing the difference DADV curve as we get closer to these magnetic impurities. The difference, it means that we are going to measure at a given point in real space, and we are going to subtract this background curve on the left. And so each of these curves that you see here correspond to a different point in real space at approaching distance to the impurity. So first at 10 angstroms, then 8 angstroms, so on and so forth. You see that far away, we find a essentially flat curve, meaning that there is no difference with the background. But as we get closer, we see that there are these little protuberance within the gap, which correspond indeed to these in-gap excitations of these Yu-Shiba-Rusinov. Okay. Here you can see it's somewhere at 1 milliev in the bias. And so if we fix the bias difference between our tip in the STM and the sample, and then we do a sweep in real space, what we find is that this excedent of states are actually localized on impurity. And this is what you see on this panel on the right, okay? Meaning that this excitation is very local in real space. And I will also should say that there appear in two of these excitations, one a negative bias and another a positive bias. They are sitting symmetrically with respect to the Fermi level. And this means that we can excite the system, we can excite the Shiba states either by adding or by removing electrons from our sample. Okay, this is a general property of superconductors. Okay, so these Shiba states, as you see, were already predicted in the 60s. They were studied in the 90s, and nevertheless they have attracted a lot of attention recently, and that's in a big part thanks to the development in the STM and atomic design. So now, beyond this fundamental interest, there are new avenues of research, new, more pragmatic interest. So let me, before starting the actual content of the talk, just quickly summarize what are people studying in this field. Okay. So the first idea, or the first line of research, it's related to the observation that studying the response to local defects can serve as a probing tool to extract information from the substrate. One good example of this is a technique called quasiparticle interference, QPI for short, where basically by studying the standing wave pattern of these scattered electrons by impurities in real space, that you see here in this plot on the left, these little wiggles, we can Fourier transform these oscillations, and then we can gain information on the band structure of the substrate. Here you have an example where we recover the Fermi surface of the substrate by just Fourier transforming this measurement. There are more recent examples and also more convolute. So for those of you in the audience who know about this topic, just let me mention that people have used Shiba states to extract the induced odd frequency pairing in conventional superconductors. And also, just to give you another example, they have used Yu-Shiba states to study the magnetic ordering in chromium diamonds, also, of course, in superconductors. This idea of using Yu-Shiba states as local probes has been taken even a step farther, and have been able to realize Yu-Shiba states in the tip of the STM, which gives us a resolution of a single state, actually, and allows us to study spin-dependent phenomena. This actually experimentally is very challenging, but people are actually able to engineer these impurities in STM. The other field of research related to Yu-Shiba states is the efforts, both experimental and theoretical, of using complex structures of these impurities in real space in order to engineer exotic states of matter, and more precisely, topological superconductivity. So in 1D, you have this change of magnetic impurities that are believed to host Majorana zero modes on the edges. So this might be familiar to you if you're working on this topological quantum computation. And there are also dimers, and there are even proposals to braid these Majorana zero modes and realize quantum gates in these systems. Okay, although I should say that this is, I mean, there's much experimental development in this area, but it is still far from being, realized in a consistent manner. In 2D, there are also impurity lattices that are proposed as a mean to engineer this topological superconductivity, and these ferromagnetic islands have been observed to host chiral modes on the edges that are also believed to be, I'm going backwards. Yeah, they're believed to host modes that are topologically protected. Okay. So to summarize these two last slides, there are these two lines of research, either using Yu-Shiba states as local proving tools or as a mean to design exotic phases. But in any case, both of these efforts require a good understanding of the properties of impurity-bound states. And this is precisely the framework of the work that I will present you next, and also of all the many works that we see in the field that address these fundamental questions regarding impurity-bound states. Okay. So now I will present you a very simple model of a magnetic impurity on a two-dimensional superconductor. That was a model originally used by Yu-Shiba-Rusinov in the 60s to treat this problem. Here you have the Hamiltonian of the system. So let me slowly walk you through it. Here in yellow you have the term that describes the kinetic energy of the electrons in the substrate. So these Ck, sigma are simply creation and annihilation operators of the electrons on the substrate, and epsilon k is the energy dispersion of these electrons in the normal state. So this is a very standard term. Then here you have the term that describes superconductivity. So we're treating it, of course, at the mean field level with a delta, this ordered parameter that we will assume it to be a degree of freedom of our theory. Okay. And finally, in red, you have the term that describes impurity. So here, J is the amplitude of the exchange coupling between the superconducting electrons in the substrate and the spin of the impurity, the magnetic spin of the impurity. So just one little remark here, this C dagger 0, it's a creation operator in real space, meaning that R equals 0 is the point where we are locating our impurity, okay? And so by treating the impurity with this model, we are actually making three important assumptions. We are treating the impurity as a local anisotropic object, so essentially just one point in real space. We are assuming that it behaves as a classical spin, so it's essentially a Zeeman splitting at R equals 0, and that means that we are neglecting the quantum fluctuations of the spin of the impurity. So there will be no quantum physics in this Hamilton. And finally, the third important assumption that we are making is that we assume that the superconducting gap is not affected locally by the impurity. We are not treating superconductivity in a self-consistent way. So these assumptions, they may seem a bit rough, but well, the truth is that this model, even though it's very simple, it captures fairly well many of the experimental observations that we see, at least qualitatively. So that's the main reason why it's actually very popular in the I should also say that in order to have a more realistic description of this problem, TIP needs to consider non-magnetic scattering potential, but this is not really important for this quasi-particle focusing effect that I will present. So I just didn't put it here to keep things as simple as possible. And so this impurity problem, we can treat it as a standard scattering problem with the T matrix formalism, where we express the change in the density states due to the impurity as the product of two Baire propagators and the T matrix. I will get back to this later, so I will not go into much detail here. Just I tell you that by looking at the poles of this quantity here, we find two in-gap solutions that correspond to these in-gap states that I show you in this experimental plot. And so to understand a bit better the physics of that is encoded in this Hamiltonian, it's actually quite useful to look at the excitation spectrum as a function of J. So essentially the energy of these poles as we change this parameter J in the Hamiltonian. So this is what I'm showing you in this plot. Horizontal axis again is J, vertical axis is energy. And here this curve represents the energy of the excitation, the energy of the Shiba. And so at very low exchange coupling, you can very easily imagine that the ground state of the system is going to be essentially an almost unperturbed BCS state where the electrons are forming these Cooper pairs and the spin of the impurity is free. Now, the excitation over this ground state, I say again, it's a single particle excitation. We consist in breaking one Cooper pair and localizing one of the electrons in the vicinity of the impurity so that it partially screens these impurities. And you can immediately see that the energy of this excited state is going to decrease as we increase J, because there's going to be a trade-off in energy between the energy cost of breaking a Cooper pair and the energy gain of having this exchange interaction between the screening electron and the impurity of the spin of the impurities. And so very naturally, as we crank up J at some point, at a certain critical J, there will be a level crossing where this screen spin state becomes more energetically favorable than this free spin state. And then we go to a situation in which this screen spin state becomes a new down state of the system. So this point is JC, is usually called the Yu-Shiba-Rusinov transition, or it's a quantum phase transition or level crossing, as you want to call it. And it's the essence of this model. And let me tell you to conclude this introductory part of the model that this transition has actually been observed experimentally. This was done by the Berlin group not so long ago, and they considered a molecule with an iron center. So this is a magnetic molecule. It's put on a lead substrate. Lead is a superconductor, and it has the particularity that it's relatively flexible. So they realized that by changing the distance between the superconducting, the STM tip, sorry, and the magnetic molecule, they could exert a force on this impurity, and they could effectively vary J. So the result of this experiment is represented in this plot on the right. The horizontal axis is the distance between the tip and the impurity, which can be mapped to our J in the previous plot. This vertical axis here is the sample bias, and the color scale dV, or in other words, the density space. So you see here these two nice coherent peaks of the superconductor, and within the gap, you see this other line to represent the Shiba state, of course, sitting at positive and negative bias. And you see that as we vary J, it goes all the way to zero energy where the Shiba transition happens. So you might complain that this is not truly zero bias, but this is an artifact of the fact that you're measuring with a superconducting tip. Okay, so one has to deconvolute the gap of the tip, and when you do that, you find that indeed this is the zero bias of the substrate. So indeed they reach this transition and they can observe this on level curves. Okay, very good. So now I'll move into this third part of the presentation, this quasi-particle focusing effect. And to motivate this study, let me tell you that one of the key observations to realize these ideas of engineering complex structures of impurities in real space was the observation of Shiba states in two-dimensional materials. So You have here a few examples. Those are all DIDB plots in real space. So the color curve or the color scale, sorry, again represents the density of states. And here where there is a maximum, that's where the impurity is sitting. There are a few examples. This is niobium selenide, where it was first observed in 2015. This is also niobium selenide crystal. And here you have a similar compound, lanthanum, and this is beta bismuth palladium. And what you can see actually is that this INGAP state, this DIDB, it extends over a few nanometers from the impurity plot. And this distance actually having an INGAP excitation that extends an INGAP bound state that extends over this distance is actually quite unusual. So those are very long range states. And the fact that they are this long stems from the fact that these materials can be considered as effectively two-dimensional. If for comparison, we overlay this Shiba state measured by Eligius Dani, the one that I showed you at the very beginning, you can see that it's much, much smaller. And this, I emphasize, is not just because the resolution was much worse in the 90s, but also because this is a bulk state. This is a 3D superconductor, whereas this niobium selenide can be considered 2D. And so the experiments that came after showed that one can actually use the fact that they have this larger extent to hybridize them and therefore build these dimers and this change in real space. But for that, one needs to have a precise understanding of what controls this remarkable anisotropy, what controls the decay and the oscillations of these shifts. And this is precisely the goal of this work, this analysis of the quasi-particle focus. So I present you this analysis in 3 parts. First, I will show you an analytical approximation that allows us to relate the shape of these INGAP excitations to the bound structure of the substrate. Second, I will show you that this analytical approximation is quantitatively accurate against calculations on the lattice, type binding calculations. And finally, I will show you an analysis of STM data with this approximation. So this is perhaps a good moment to stop if there are any present questions or anything I said so far. Don't see the chat here. I guess no.
I would like to ask one.
Yes, please.
In the last slide of the previous section, the experimental observation, what is exactly a Shiba transition?
So the Shiba transition, maybe it's better if we look at it here, is the point where there is a level crossing between the ground state and the first excited state. So you have to distinguish between these two states. Ground state, the spin of the impurity is free, and then excited state is by a binded electron. So at some point, as you crank up J, this state becomes more energetically efficient, and there is this level crossing. And how is this level crossing manifested in an experiment? Well, the excitation goes all the way to 0 energy. And this is what they observed in this experimental plot. So this is the INGAP excitation. You see that it goes, it moves to lower bias energy as we vary this J distance, and it hits this point that corresponds to the 0 bias point in the sample.
Okay.
Does that more or less answer the question?
Yeah. No, you have said it, but
okay. No, it's fine. Yeah, thanks.
Thank you very much.
Thanks for it. Okay, so if there's not anything else, I'll continue presenting this quasi-particle focusing. Let me start by telling that this effect was actually already known in normal metals. So let me quickly summarize the main idea here. You have here a experimental plot of the local density states in a copper surface around a cobalt impurity. And what the analysis of this measurement tells us is that the response to this defect is preferential in directions perpendicular to the flatter sections of the thermocell. Okay, so let me just say that again more slowly. Here you have 2 plots of this that exemplify this statement. On the left, you have the real space response. So this is where the impurity is, and this is the change in the local density states due to the impurity, these little wiggles here. And on the right, you have the thermosurface of the substrate of copper in this case, where the color represents the curvature of this thermosurface. So when it's more warmer, it means that the curvature is smaller, it's flatter. And so you see indeed that this response here is along directions such that the Fermi surface is flatter. It's perpendicular to these flatter segments of the Fermi. So the key point to take away from this slide is that there is this non-trivial relationship between real space response and momentum space properties. And this analysis was done by means of a saddle point approximation on the normal metal propagator. I will explain in a second what this means. And what we did here was to generalize this for Shiba states and for the case of superconductors, which, as we will see, is a bit sad. Okay. So for the analysis, let me just recall that the change in the local density states due to the impurity can be essentially be written as the product of two propagators, G0, that goes from the point where we evaluate the impurity to the impurity and then back from the impurity to the point where we evaluate the propagator. Then we have this object here, which is the T matrix. This depends on the energy. Here, this energy is the energy of the Shiba state, of course, and it essentially encodes all the multiple scattering processes that occur in this phenomenon. So namely the fact that the electron goes once to the impurity, it's a scatter, and then it's a scatter twice, it's a scatter thrice, and so on and so forth. You have all these virtual scattering processes encoded in this T matrix. Here, by the way, in this cartoon, theta r is the angle on the plane of this r vector that determines the point where we evaluate and we're changing the local density. And so the key point here is that as we are assuming the impurity to be fully local, all the information, all the spatial information of the response to the defect is encoded in these bare propagators, in these bare green functions. So that means that the T matrix does not depend on K and it does not depend on R either. Therefore, the only thing that we have to do to know the response in real space due to the impurity is to do this Fourier transform. So mainly, this is the bare propagator that we can trivially write in momentum space, and then we just go to real space by Fourier transform. Just one little detail here. This is a matrix, so this might be a bit surprising for you. It just means that we are working this particle Hall space for superconductors. So here the spin degree of freedom is not important because, well, our Hamiltonian is diagonal in spin space, and this 2 by 2 space is the particle Hall. But this is just technical detail that is not so important for the discussion. And the point is that we want to calculate this green function for an arbitrary energy dispersion that encodes the anisotropy of the substrate. Again, I emphasize that our goal is to understand the anisotropy of the in-gap. And this integral is in general very difficult to solve for a generic epsilon k. So what we'll do is to do a complex saddle point approximation, where essentially we are going to replace this integral by the points in k space that contribute the most to the propagator. Okay, these points here we denoted kj, and they depend, of course, on theta r. They depend on the point where we are making our measure. I should say that this approximation will be only valid far away with respect to kf, of course. And here you have the result of this analysis. So the analysis is telling us that this propagator can be approximately rewritten as 1 over this power law decay that is isotropic, and then a sum over this complex critical J, and then this term here. So this term is, we have a geometrical prefactor, and then we have the exponential evaluated at this complex kj. So the real part of this complex kj will give us a Friedel-like oscillation terms. It means that our response will oscillate in real space. And the imaginary part of this complex solution will give us an exponential. And this turns out to be crucial, and it's a very important difference with the case of normal metal response, where you don't find this imaginary term and you don't find this exponential. And you can, in a sense, understand it as the natural result of evaluating a gap propagator at the energy of the Shiba state. So in a sense, it's not so different of the case of evanescent states in electromagnetism, where you also find this exponential. Okay, so to understand a bit this expression, let me actually open here a parenthesis and let me walk you through the main idea of this complex saddle point approximation. So this might be perhaps a bit technical if you're not so much interested, but I thought that it would also help to clarify where is this expression coming from. Okay, sorry, where is this expression coming from? So it might be worth to just detail it a bit. The integral that I showed you before can be seen as a function times an exponential with a large parameter index. So what we are going to do is we are going to deform this integration path so that it goes through a saddle point of this function index point. And why a saddle point? Well, because it's a property of these complex value functions that through a saddle point you can find a path that goes over the maximum of the real part of this function phi, while at the same time it goes through the constant path of the imaginary part of this phi. So that means that this maximum of the real part will give us the largest contribution through the exponential, while at the same time, the fact that the imaginary part is constant will ensure that we don't have wild oscillations that are killing off the contribution to the integral. So once that we have this new integration path, we can just proceed with the standard Laplace method and then develop the exponent to second order and do this Gaussian integral that gives us this result, where basically we have a prefactor that depends on the second derivative of phi, and then we have the integrand evaluated at the solution of this equation, the saddle point, the critical part. Okay, and this procedure can be generalized to n-dimensional integral as it is. So if we go back to our propagator, I want to bring your attention to this, of course, complex, and then we have here the denominator. We just introduce a new integration variable to promote the denominator to the exponent. And the key point here is that R is going to be our large parameter, meaning that this approximation will be valid far away from the impurity. And second, you see how this function here is encoding the anisotropy through this unitary R vector in real estate. Okay. Then we just proceed with this standard Laplace method. As I told you before, this gives us this result. But what is crucial here is that the solutions to this, the k points where we are evaluating this term here, are going to be given by this saddle point equation. So namely the gradient of this function equals. So you can immediately see that if I evaluate my propagator at a different point, then I will have different R vector here, and I will have therefore different solutions to this equation. And then I will have a different propagator here, different approximation for the propagator. So this is what is controlling the anisotropy. So implicit equations are perhaps not so important, but I want to bring your attention to the first one, where we have on the left-hand side the energy dispersion evaluated at these kj solutions. And on the right-hand side, you have I times the square root of delta. I recall that delta is the gap of the superconductor, and then minus E squared, where E is the energy of this Yu-Shiba state. So this is actually also very enlightening because you can immediately see that if E is smaller than delta, as it should be for an in-gap excitation, then this square root is real, and you see that times I gives us an imaginary number on the right. So the energy dispersion is naturally a real function. So in order to have it equal to an imaginary number, it necessarily means that these kj's have to be complex solutions. So again, this is just to emphasize that the complex nature of the solutions to our saddle point equation stem from the superconducting nature of the substrate, and they are not present in normal. Okay. Okay. So now let me close this parenthesis and go back to the main story, where we have a more physical look at this approximation, this solution. To make some sense out of these complex saddle points, we are going to take the perturbative limit of delta being much smaller than the Fermi energy, which is reasonable for this. Well, it's reasonable for the superconductor that I mentioned at the beginning. And within this limit, it turns out that the solutions to our saddle point equation can be related to two real saddle points that I denote here k tilde. And they are such that they are sitting on the Fermi surface where the Fermi velocity is parallel and anti-parallel to the observation direction. So this recipe can be better understood with a little cartoon. So here you have a rather anisotropic Fermi surface, And on top of that, you have this R vector in real space, the point where we evaluate, this goes from the impurity to the point where we evaluate our propagator. And these k tilde plus and minus are sitting on the Fermi surface where the Fermi velocity that is indicated by these small arrows is parallel to R. And you can immediately see that if I evaluate my propagator at a different point, I'm going to have different R, and these k tilde plus and minus are going to be at a different point on my front. Now the question is, how do we relate this k tilde to this expression that involves these complex quantities? Well, the characteristic oscillation length that is related to the real part of the critical point solution here in blue is going to be just 1 over k tilde. So that means that it's just as an angular dependent Fermi moment. Then the exponential decay, which was related to this imaginary part of the critical point, is going to be proportional to the Fermi velocity evaluated at this k tilde over this term here that is on the order of that. And finally, the analysis tells us that this geometrical prefactor is just 1 over the Fermi velocity times of the curvature of the Fermi surface, both of them evaluated at this k. So again, let me just recap. The main idea is that as I evaluate my propagator at a different point, I have different k points that contribute the most to this propagator, and therefore I have a different expression here, a different approximate expression in real space. This is what is controlling the anisotropy. Now, if you look carefully at these two expressions, you might notice that this exponential decay is proportional to the Fermi velocity, and this prefactor goes as 1 over the Fermi velocity. So one might expect some sort of competition effect, but I will show you now that this is not the case, and this will turn out to be important in our analysis of STM data. Okay, so this just keep it for later in the presentation. To analyze that, let me just consider an isotropic energy dispersion, which I'm represented here. This is a plot in K space. And here the Fermi surface is represented by this dashed red line. So the Fermi velocity is given by this green arrow. So I recall that it's essentially the gradient of this energy dispersion perpendicular to the Fermi. And so we are going to consider an area preserving transformation in which we are essentially squeezing this energy dispersion along the x direction. So after doing that, the Fermi velocity is enhanced by this factor gamma. You can already see that here the contour lines are closer together, meaning that the gradient is steeper. And at the same time, along this direction, the Fermi surface became flatter, meaning that the curvature is small. And the analysis tells us that the change in the curvature actually compensates the change in the Fermi velocity, so that in the end, both the decay length and the prefactor are enhanced along this direction. And conversely, if we look along the y direction, they are both decreased because the opposite effect is happening for this transform. So the takeaway message from this is that both the decay length and the prefactor are in phase, meaning that they have the maxima at the same points and the minima at the same points in the same directions. And therefore, we don't have competition effect between these two terms controlling the isotope. Okay, so now I will move to show you how we can apply this approximation to treat tie binding calculations. And for that, let me start with a very simple toy model of nearest neighbors hopping on a square lattice. So this model has the advantage that allows us to interpolate from a very isotropic Fermi surface into a very anisotropic one just by changing the chemical potential. And so here I'm showing you the local density states calculated numerically. This is a plot in real space, and at the center is where the impurity is sitting. You can already see that in this case it's very anisotropic. But to make a more quantitative statement, what we are going to do is to extract the decay length by fitting radial cuts of this numerical data. So this is what I'm showing you here. Each of these dots represents the decay length extracted by fitting the LDOS to this expression here, to the envelope, the power law times x bar. And to compare with the analytical approximation, we are going to evaluate the Fermi velocity at the corresponding k tilde for each direction. And this is what we are representing in this solid line underneath. So here and there. So you can see that in both cases, there is a very nice agreement between the two. Okay. And finally, let me just show you the plot of the prefactor. This is calculated analytically. Unfortunately, we cannot extract it from a fit, but it's also insightful to look at it. First, because you can see that it's indeed in phase with the decay length. As I said before, they have the maxima and minima along the same direction. And also, it helps us to understand why the anisotropy of the Shiba state looks this way. Namely, if we look along this direction, this x equal y direction, the diagonals, the critical points are going to be sitting here and there on the Fermi surface. So that's where the Fermi velocity will be the largest, and therefore we'll have a higher decay length. And also where the Fermi velocity, the curvature of the Fermi surface will be the smallest, it will be the flattest, meaning that we have an enhanced free. So again, to summarize, it is the interplay, the combination of these two quantities, Fermi velocity and curvature, that controls the anisotropy of the shields. Okay, to push this approximation a bit farther, we are going to apply it to more realistic material. So particularly we consider niobium diselenite. This is a TMD, a transition metal decalcogenide. I believe that in the previous seminar, these materials were discussed at length, so I will not say much now. Just let me tell you that we can describe them with a fifth nearest neighbors tie binding energy dispersion on a triangular lattice. Okay, and so this energy dispersion gives us this Fermi surface. So here the hexagon represents the first Wilson zone. We have gamma, k, k prime, and we find that there's 3 inequivalent pockets in this Fermi surface, which are of course disconnected. So even though this Fermi surface is slightly more complex than the ones I showed you before, we can proceed with an approximation of the same, meaning that for a given direction in real space, each pocket is going to contribute a pair of these critical points, k tilde plus and k tilde. So in total, we will have 2 per pocket, meaning 6 critical points for each direction. Now, if we want to calculate the local density states, which I say again is the product of each 2 propagators, each of them contributed by 6 critical points, we are going to have a rather complicated table with 36 interference terms, right? 6 terms from the incoming excitation, 6 terms from the scattered excitation, and then all the interference make up 36. However, far away from the impurity, where this approximation works better, by the way, it will be the terms with the largest decay length that we dominate. And for that, it's important to realize that the decay length of the elders is going to be the harmonic mean of the decay length of each of the propagators. Okay, this is expressed. So this harmonic mean rule tells us that it will be in fact the process corresponding to this diagonal, or in other words, the intra-pocket processes that will dominate far away from each. So this just to say that this analytical approximation, or another of the interests of the analytical approximation, is that it gives us an extra insight on what are the scattering processes that give rise to this Shiba. Okay. So that's just to pinpoint why we are interested in having this. And finally, to compare it against numerical calculations, we do as we did before. We calculate numerically the LDOS. We extract the decay length by fitting the envelope to this power law times the exponential. This is represented by these dots. And then we just evaluate the maximum of all those Fermi velocities at the corresponding k tilde, and then which is represented here by this solid line. And again, that you see that even though the Fermi surface is more complex, we still have a very nice agreement between each. Okay, so in the last 5 minutes, I would like to show you how we can apply this approximation to treat STM. Here, first thing that I like to say is that we are running into a bit of a challenge. And this problem that we find is that since the gaps of these compounds, these superconducting TMDs, are very small, they are on the order of the 1 MeV, the typical superconducting coherent length, which gives us the order of magnitude of the decay length of the Shiba state, are going to be rather large, on the order of the 50 nanometers. So this 50 nanometers is unfortunately much larger than the typical field of view of an experiment. Here you see that the typical STM picture is about 1/4 of this distance. and also it's larger than the typical inter-impurity distance. We see here that there are many of these impurity bound states that are closer to them. So that means that we cannot reliably fit the radial decay of the LDOS to this point. We cannot extract from this short distance the exponential decay. But the good news is that as the prefactor and decay lengths are aligned and there are no competition effects, we can actually forget about this exponential decay length and consider the prefactor. Okay, and what we will do now is to extract the anisotropy of the prefactor in this experimental data and compare it against the analytical approximation. So for that, let me recall that within our model, the LDOS is essentially the product of these three terms. We have the prefactor that is angular dependent. Then we have an oscillation, an oscillatory term with a typical characteristic length of lambda. And then we have this power law times the exponential with a typical characteristic length xi that of course also depends on. And this prefactor is related to the Banach structure of the sample, in this case, niobium selenide, through this expression that depends on the Fermi velocity and the curvature of the Fermi. And so the idea of the analysis is to consider an annulus of data around impurity, which is indicated in this plot on the left. And we are going to integrate it radially over a distance delta. And we are going to compute this quantity here, and we're going to make two important assumptions. The first one is that we're going to suppose that this annulus is wide enough so that when we integrate, these oscillations are averaged out. Okay, so that means that this delta has to be longer than lambda, the characteristic oscillation. At the same time, we are going to assume that this annulus is narrow enough so that the exponential term is essentially constant, or means that which requires that delta is smaller than the typical exponential decay length of some. So when we do these two assumptions, it turns out that this integral here is actually independent of delta, and more importantly, is proportional to this prefactor, that is the quantity that we are interested in extracting. And therefore directly related to the Banach. Okay. So this is what we are going to do. Here I'm showing you the final result of the analysis. On the left, you have again the data that we are analyzing. We are fixing R0, which is this green circle here, and then we are integrating for increasing values of delta. So there are all these concentric circles that you see here in warmer colors. On the plot on the right, I'm showing you the integrated signal as a function of the angle in real space. And first of all, you see that all of these warmer colors, they collapse onto more or less the same universal curve, meaning that indeed this integrated quantity is independent of delta, and this supports the approximations, or the assumptions rather, that we made in this slide. And what is perhaps more interesting is that when we overlay this data with the analytical prediction, which is the blue curve, we see that there is relatively good agreement between the two. So the first nice thing about it is that the relative shift between the blue curve and the experimental data points is not a degree of freedom. So this is actually extracted by looking at the topography and the lattice of the sample and relating that to the actual orientation in K space, which controls this blue curve. And also, more interestingly, you see that this blue curve, the model, captures these non-trivial harmonics in the experimental data. So namely the fact that here in the valleys where the signal is weaker, you see that it's actually wider, whereas here in the peaks, it turns out to be more narrow. So this actually is at least qualitatively captured by this analytical prediction. And in that sense, it constitutes a success of the system. Although, of course, many approximations were done through the way, and it remains qualitatively compared. Okay. Okay, and with that, I'd like to conclude. So just very briefly, let me recall or recap the first part of the presentation. I told you that there is this difference between non-magnetic and magnetic defects in conventional superconductors. Only magnetic defects have a relevant or important effect in superconductivity in small quantities. because they break this time reversal symmetry. And in particular, when we have this one defect, it binds these in-gap excitations that are called Yu-Shiba-Rusinov. So these Yu-Shiba-Rusinov states in real space, they exhibit and mark anisotropy. And we show that this anisotropy is controlled by two parameters in the substrate, namely the Fermi velocity and the curvature of the Fermi surface. And second, we show that this analytical approximation agrees quantitatively against these time mining calculations. And finally, which is perhaps more interesting, is that we can access the prefactor in the STM data and compare it also against this analytical approximation. And with that, I'd like to conclude. I'd like to thank, of course, Pascal and Andrea, that are the advisors that also work in this project, and Frédéric Massé and Tristan Krent from the LPS and the Institut de Neurosciences de Paris that provided all the data that I show you here today. And with that, I thank you for your attention, and I leave here the conclusions again in case well, there are questions about. So.
Okay, very nice, Mateo. Let's see if there are questions. I have some. Let's give a minute, otherwise I can start with mine. Okay, so starting from the end, it looks like a really nice result. I mean, most of us theorists don't get to a point where we are actually able to feed experimental data with our theory, which is something I think it's nice. I mean, am I fooled by the fact that I'm an outsider to the field? Or how impressive is the fact that you can feed that experimental data?
Well, okay. So as you say, in general, in this condensed matter, I think measurements are very dirty. There is many things that we don't control, and there are many strong approximations that we have to. So, in that sense, I would say that, well, it's an interesting result. In this field of Shiba states, you can see that there are more and more people giving a precise analysis of STM observations. So the field is rapidly evolving, and one thing that is actually very that we get now better and better resolution with the STM. So people are starting to use superconducting tips, and this gives you access to well, better data, and then you can hope to with better results. And then another maybe thing that is happening that allows us to also get better fits between theory and experiment is that people are making more refined models. So this model is actually very rough. Impurity is local, it's classical, but people are starting to use more refined models when fluctuations are taken into account. And I would say that we are seeing more and more you know, comparison between theory and experiment in that sense. So to answer your question more shortly, I think, yeah, it's still nice. It's still a challenge to analyze STM data, but I think that in this field we are seeing more and more often.
Okay. And what would be the goal? Like, so now you have this model that is able to feed this spatial data. Well, would you like to, I don't know, to predict this spatial conformation of the density of states, or the opposite, or have the spatial conformation and work backwards to extract information about the dispersion relation? Or
well, absolutely, that's an extremely good point. I think, well, the next step would be to consider what happens if your gap, for instance, the superconducting gap, is K-dependent, and it's not this trivial S-wave that we consider. How is this reflected on these local density states, on this anisotropy? And most importantly, whether we can use it to say something about a gap, meaning that is it possible by looking at this Shiba picture to tell if we have unconventional superconductors, for instance? So yes, okay. I mean, I think it would be very nice to push this further and see if we can work backwards and extract information on the superconducting payload.
Okay, nice. I have other more trivial questions, perhaps. When you say, so you commented on the fact that when you have bulk material, the decay of this density of states around the impurity is fast, and for 2D materials it becomes long range. When you say long range, I mean, long range is a very abused word. Sometimes it is used to mean that you switch from an exponential decay to a power law decay, but in this case, you've shown that the decay of this long range density of states is exponential and power law. So what does long range mean?
So long range precisely means that the dimensionality of this asteroid is encoded in this power law prefactor. So for 2D materials, it goes as 1 over the square root. For 3D, it goes as 1 over r. Okay, and this has, especially in the close to the impurity, has an important impact. You can see really the difference.
Okay.
But just to emphasize, in both cases there is exponential decay, both in 3D and in 2D. Yeah.
Okay. And then curiosity, in these plots where you show the density of states for 2D materials, it seems to be maximal at the site of the impurity. And if I recall correctly from the introduction, when you showed it for the bulk material, it was localized around the impurity, but it didn't have a maximum right at the impurity.
Yes, that is absolutely true. You can see it here already.
Yeah.
So, well, the honest answer is that I don't know. In general, knowing what is going on with the local density states on the impurity side is very difficult. The model of assuming a delta, a Dirac in a completely localized scatter is not going to be valid anymore. You're going to need to reflect, well, the geometry of the impurity, how it's absorbed, possibly also its orbital nature, and it certainly influence this what is going on the short field range, right? In particular, for this case, I don't know what really controls this in the manganese, but in any case, I'm pretty sure it is not related to the dimensionality of the sample. It's just a coincidence here that it looks at it maxima. You can already see here in this beta bismuth palladium that it's also a bit
that's true,
displaced from the center. But it will depend on many details of the impurity.
Okay. Well, if there aren't any more questions, we might as well end it here. Thanks a lot, Mateo, for the talk. I really liked it. I think it was it was difficult to ask questions because I felt like it was very self-replying, in the sense that you opened questions that you later closed yourself, which I think is nice.
Okay, I hope it was clear. But yeah, thanks a lot. Yeah.
Thank you very much. Thank you.
Thank you. Bye.
See you guys at some other point. Cheers.